Okay, I think we should get started. Thank you very much for coming to my talk, which is called Oh No, More Modern CMake. My name is Deniz Bahadir. I'm working at Benox, a small company located here in Berlin, where we try to speed up the internet and help the big and smaller internet service providers to analyze what's happening in their networks. But if you want to know more about that, come to me after the talk. Now we are going to talk about CMake. And I'm not sure if you know that, maybe the older ones of you know that, the title resembles a computer game from the early 90s. Some might realize that, and I'm not sure if you know this figure there. It's called Lemmings, and there was an expansion pack for it, was called Oh No, More Lemmings. And in Lemmings, you had to help your small lemmings to reach your goal and don't fall into any pits. You had some features for that, and similar to that, I'll try to show you some features that CMake will give you to reach your goal, to build your targets, and a link to that without falling into all these pits. So there are problems, but there are ways to get around them, and I'll try to show you some of these in this talk. I gave a talk last year here at the very same conference, which was called More Modern CMake. Is anyone here, maybe show of hands, who's seen that either live or online? Okay, some, that's good. If you know that, that's a very good start for understanding this talk. If you don't, you probably should leave now and watch it online. No, you don't do that. You can watch it later if you want to. It should be understandable, I hope, for everyone, but if you know that, that's not bad. And to just show you a little bit what I did there so that you know what we are talking about here, a short recap. And the first thing that comes up every time for especially new developers is what is CMake, and especially what is modern CMake, what makes it modern. CMake itself is a portable build system generator. The emphasis is on generator. It's not a build system because it generates the input files for other build systems like Make, Ninja, or Visual Studio, or whatever you want to use and which CMake hopefully supports. And it supports several languages, most prominently, of course, C++ and also C, but also some others like Fortran, C#, CUDA, and there are even more. I don't really know what these are all, but it's possible to find it out. Okay, and modern CMake, this term was coined in 2014, and it's pretty much what could say it's modern CMake exists since version 3.0 of CMake. But then some people might complain, no, it's actually 2.8.12 to be precise. And 3.0 was just a version which made it somehow incompatible with former versions, but let's just stick to 3.0, it's easier. With the 3 in front of it, it looks nice that it's starting from there. And the main thing about being modern is the target-centric approach. Because in this way now, CMake, all the targets that you declare in CMake for building something carry their own build and usage requirements with them and will also propagate these. And also, of course, as is probably with all programs, each new version somehow improves what it does, and this is also what CMake does. But the nice thing is, to the new features, there also very often come some simplifications. And that's also some things that I want to show you that I already showed you last year in this talk, but which I will also present you here. In the last talk, we learned 2 very important terms, and these are the ones that I already mentioned. It's called build requirements and usage requirements of a target. And what that is, it's just what the name says. The build requirements is everything that you need to hopefully successfully build the target, while the usage requirement is everything that you need to use that target if you declare a dependency on that target from your other target you're currently building. And these requirements are pretty much the same, starting with source files, which in general are just build requirements, not the usage requirements, but sometimes they can also be usage requirements. But all the other things you see there, they include search path, where you find your headers, some predefined preprocessor macros, some dependency to libraries you have to link, and all this stuff. These are usage requirements and also build requirements. And you see that here. I don't have to read it out loud, I hope. I showed last year this table to compare the traditional CMake way with the modern CMake way, and the differences here, we'll just go through that real quick. The build requirements, where you set them on, in traditional CMake you do this on the environment, so mainly on directory scope, so it counts for this directory and all targets in this and subdirectories. While in modern CMake you can be more specific and set the requirement on a specific target and it counts for that. And you can also set it on some dependencies, but okay, that's just a special thing there. Keeping track of these usage requirements. In traditional CMake you use variables, cache variables or normal variables, while now you don't have to keep track of them because the targets do that themselves. And the propagation is done using the targeting libraries command. That was similar for both versions. With targeting libraries, you declare a dependency from one target to another. So you say target on the left-hand side depends on the one on the right-hand side in that command. And the propagation of the usage requirements from the target on the right-hand side was explicit by hand, to be done explicitly by hand by you, the developer. While with modern CMake, in general, you shouldn't do anything else except for just having the targeting libraries call. And in general, one could just say, traditional way, you had to do more stuff, and so were more possibilities to make some errors. While with the modern way, you have the chance to get away with less errors, or hopefully none. And it also allows a more fine-grained configuration. Okay, and then of course, you want somehow set these build and usage requirements on targets. And for that, we have this the so-called target underscore something commands. I recommend to, in general, always use these. There are some others, but that's pretty much what you should use there. Currently, there exist 9 things, with the newest one being the target precompile headers, which allows to declare some target for, what it says, precompiled headers, so to precompile them. And the important thing is, if you want to set the build requirements, use the keyword private between the target and the dependency. And similar to that, if you are declaring the usage requirements, use the keyword interface. Then logically, if you want to set both, there's also a keyword for it, which is called public. And you should then use that. These are the commands that you should use. There's one of them that sticks out a little bit, and that is target link libraries, which I already mentioned on the slides before. This one is pretty old, and it works without the keyword. But I really recommend you should never use that without the keyword. We will see in this talk a situation where we can't do it with the keyword. But in general, never omit that keyword, because the other targets will complain that it's missing. Targeting libraries will not. It will just do his thing, but it's not exactly what you expect. It's still working somehow, but it's doing something a little bit different, and maybe that's not what you want. So never omit that. Okay, and that's pretty much what modern CMake is on a very fast scale. And if we go further now, there are some things I showed you last year, which I recommended to use, and these have evolved and changed a little bit, and I will show you these real quick. For example, last year I recommended to always use the target sources command if you want to add sources to some target, and that's still something I would recommend. In general, you see it on the right-hand side. If you declare a target, you probably use the add library command. Give it some name, and then the type. In this case, it's a shared library. And with the shared library, you could just add the target, the sources behind it in the same call, but don't do that. There are some other calls of add library where you can do that, and it's even better to always use the target sources command, because there you can specifically saying, okay, this is a private target, so this is a build requirement. I need that to compile it. To compile the target, while this other one is an interface or public dependency. So The interface one is not needed for building. It's a user requirement. It's for the one using it. And public, as I said, is for both. And what you could do there is to be more specific and also give the headers there. The headers you don't need actually for building, so you don't need that there. I mean, you need it for building, but not to declare it there. But it's better if you do that, especially because some of the IDEs you might use will show you that these headers belong to the target. If you don't put it in there, that wouldn't be done. And also maybe there might be some positive implications in the future if CMake changes and does something useful with that situation. And yeah, as we see that here on the right-hand side, there's the directory structure I'm showing you for this example. And so there's the parent directory where I declare the target, and there's also a subdirectory where there are some probably conditional sources that I'm adding. That's the CMake list files to see there on the bottom. And that's something that was new last year, that you could use that, or it's not completely new, but still you can use the target sources command to add targets, to add sources to your target that are in another directory, and doing it also from another CMake list.txt file. And that's a good thing. The problem is, however, for the things that are going into the usage requirements, you have to be explicitly saying, hey, this should be an absolute path, because if you're not doing that, you're just giving a relative path. The target that receives these usage requirements later for its build requirements, when declaring a dependency on that one, will just try to look it up and look it up relative to its own directory, and there it will not find it, and will will be problematic because it will fail, obviously. And so you have to add the default thing there, the absolute path there, with using the CMake current source there. However, it's even getting worse. For the build targets, as I said, as they are just used to build that specific targets, the build requirements, the sources there, you don't need to do that because it should be relative. But it's not completely. If you look it down here at the other directory, the subdirectory, there, even if I'm just setting the build requirement, I have to set it relative to the directory where I have the add library call. And that's really tedious and error prone. But luckily with CMake 3.13, that one was fixed. And now you can just use relative path everywhere. It makes your code look easier, simpler there, and it also will work correctly. So you can just omit the CMake current source dir, because everything is assumed to be relative to the CMake current source dir, which is the directory where the currently processed CMake list.txt file is located in. And they will be stored as absolute path internally, so that other targets that declare dependency here will just be fine and link successfully. So that's one thing that got improved. And the other thing, oh my, object libraries. I'm not sure if you know the story there. They were some special beast at the beginning. And then several people said, why can't we handle these like normal other libraries in CMake, other library targets? And so the developers and maintainers thought about it and found some way how they should behave. And I don't know why, but nobody was either able or wanted to implement that. And then at some point, I needed this, and I tried to implement it, and it was luckily successful. So nowadays, we could just say object libraries are like any other targets in CMake, except when they are not, because they are still a special beast, because of the definition that was given, and that's how I had to implement it. And to see it here, if you declare an object library, you do it with the add library command, using the keyword object there. Of course, adding the sources using the target sources command. Maybe also some other usage requirements here, like the include search directory or some preprocessor definitions. But there's some special thing now, and these are the object files, because different to all the other targets in CMake, this is not one specific file at the end. That's just a handle for a collection of object files you're compiling this in. And at the end, you have to link your object files into your executable or into your library that you will later link somewhere else. And so the object files are something that's new to the usage requirements. And the propagation of usage requirements and object files is different. And we will look at this real quick. And the difference here is also, it depends on what side of the target link libraries command you put the object target. Here we have the example where we put it on the right-hand side of the keyword, and we have 3 times the same code. The only difference is here the keyword in the middle of the targeting libraries command. If we look at this real quick, we declare an object like we did on the slide before, setting some usage requirements. We don't want to look at that again. Then we create some other target. In this case, it's a shared library. Give it some sources. That's fine. And now we declare a dependency from that library to that object file. So that means these object files should be compiled and linked into this shared library. And then at the end, we just create our executable and declare a private dependency. So it means it's a build dependency on that library. So that means this library has to be linked to that executable in order to successfully run at the end. Okay, and we have 3 cases here, which is in the middle, prominently there, we are just setting with the interface keyword the usage requirements, while on the left-hand side, with the private, we are setting the build requirements, and on the right-hand side, with the public keyword, we are setting both. And now the question is, how do the usage requirements and object files getting propagated up till the executable? And if we look at the usage requirements, there's no change to all the other targets. It's always the same. If I'm using the private keyword, that means set the build requirements only, so they are going into the library, but are not further propagated to the executable. Similar, if I'm using the interface keyword, it's going not into the library, but the library will propagate it further to the target, which is a dependency of, and so that means it goes into the executable. So the executable, in this case, we had the include search path, etc. This will know where it can find these headers, and it has also the preprocessor macro defined that we've seen on the slide before. And with public, that's just some kind of union. It's going into the build requirements and it's also propagated further. That's how it is for all the propagation of usage requirements, no matter what kind of target it is. That's always like that. So that's easy. Now with the object files, that's a different thing. On the left case with the private keyword, that's similar, because we're saying, okay, we are making these object files the build requirement of this library, so putting it there and not further propagating. That's fine. With the interface keyword there, we are not propagating anything, and neither into the build requirements or transferring it further. And with the public, it is as if you had used the private keyword. So they can only ever go into the build dependency, not into the it can always go into the build requirements, but not into the usage requirements. And the reason for that is to prevent you getting multiple linker definition errors, something like that. So if you are linking this to one file and then to another file and target, and then linking this together, you would get the object files twice, and the linker will complain there. Some people argue, why isn't CMake taking care of that, just removing duplicates? And that's a good question, but currently that's how it is defined, how it should behave, and that's how it is implemented. But this is something that a lot of people think it's weird, and they always come across that and don't understand it at the beginning. That's something you should keep in mind. Now that is the case for having the object file on the right-hand side of the keyword in the targeting libraries command. So obviously, what is the case if we have it reversed, so it's on the left-hand side? But then, I was ahead of myself, there's a special case before. What is if it's on both sides of the keyword? So here we replace the lib with an object 2. So we are creating a second object library, and that's declaring a dependency on our first object, and the second object library is then further linked into the executable. And the thing is here, as I said, the usage requirements are still the same, but for the object files, that's quite simple, by the way. There's no propagation of object files at all from the original one to the left, or any further. And the reason for that is object files, to compile an object files, you don't need the linker, you just need a compiler. So there's no link step. So there's nothing that's needed to be linked, so why should I put the object files any further that should be linked into that? Doesn't make sense. And at least that's how you should think about it, because that's how it is. And so just remember, if you have object files on both sides in the targeting libraries command, there's no propagation of object files from right to left. Of course, the part here, linking the object 2 into the executables, that's our first case. So it's on the right-hand side. So these are out further given to the executable, but not the one from our first object library. And what I already said, what is if it's on the left-hand side? Now that's a little bit special, because here, as I said already, for this case, it's still our first case. We are on the right-hand side. But if we look at that here, it's just on the left-hand side. So actually, usage requirements still no problem. But the object files, there is no propagation from the very first thing, which here is a library, to the left. That's just in the second targeting libraries call, which we already handled. So instead of looking at the object files here, we are looking at the link dependencies. So something which in general is the normal usage requirements thing. But now, so that means the executable at the end, should it link to the library? Because our object target has a link dependency somehow declared to the library, or should it not? And the answer is, if you're using the private keyword, there's no propagation at all. As I said, object files do not have a link step, so there's no point in using that. While with the interface and public keyword, it is propagated, but not into the build requirements of the object, just into the executable. And that is something that has changed lately, and for good reason. And now it's all the same. So that means if you're somehow declaring a link dependency there to a library through that object file, this link dependency has to be further propagated, or it's just useless in some cases. And so that was changed with CMake 3.14. And you might notice now it's still complicated. And now I have a photo moment for you. Maybe that helps you. Here's all these things together again. So usage requirements, 3 times the same stuff, no matter where you have the object file, if it's on both sides, on the left or right-hand side. And then for the other 3 cases, we have the separate things here. That's just something you should probably try to remember, or always look up this slide if you're not sure how it is. Maybe you can even convince the developers and maintainers of CMake to change that behavior, because there are a lot of people complaining about that. Especially if you think about it, why is the link dependency to the shared library always propagated, but not the link dependency to the object files always propagated when you declare dependency between 2 object files? So that's always something that's still debatable, and yeah, we will see how it's evolving. Currently, I would say it's probably staying like this for quite a long time, but we will see. Maybe someone comes up with some good way and doing it, and then we are just happy. Okay, that were some features that I showed you last year and that have changed. And now I would say let's get to something completely different, but it's not completely different, but a little bit. So I realized here, talking with some of you during the conference, how should I start doing that? I'm just clicking in my IDE and it generates me some CMake file, and then I want to change something and I'm adding that. How should I do that? And actually, I'm not using the IDE. I don't know. I know how you might do it if you started from scratch, and that's my recommendation now. You probably know that you always have to use the CMake minimum required keyword at the very top of your top level CMake list.txt file to tell CMake in what compatibility mode, what version it should support, should run now. And that's how it looks nowadays. As I said, it's required on the top level CMake list.txt file, but there's no problem if you put it in any if you want to. And there's a good reason for that. And that is if you, for example, have a big, maybe monolithic project, and at the very top you have your build system, and you have to check out everything and then compile everything from the top to bottom, or at least CMake everything, even if you just want to have some small project which is just below there. If you don't want to do that, you can just check out this small project, and if its CMake list.txt file contains the CMake minimum required keyword itself and does not depend on some of the variables or whatever that might be declared in the CMake list.txt files that are further up, then you can make that one a new root and just compile that, and it should work. Of course, that enforces some discipline on you to make it right, but that's a possibility you could do. So in general, there is no big reason to to not set it in every file. What it does, I already said, it sets some compatibility mode of CMake, but if you want to change it afterwards, maybe conditionally or so, if you're saying, okay, I'm supporting at least CMake 3.5, but if you are using CMake 3.9, I can use this cool feature, then you can set this with the CMake policy to modify the current version for some of the policies and tell CMake, okay, here you should use some different behavior for this special feature, which comes from a later version, for example. And there also exists scopes, so that's nice that you don't pollute all your CMake files with it. And the version range you see up there, that was new in 3.12, and the thing is, that's luckily backward compatible. So if you're using a version which is older, it will only see the first part of the version and assume the rest is just some subversion parts. And if you're using a recent version, it will realize, okay, I can use, as a minimum requirement, I have to use the, in this case, 3.15 version. If I myself am just CMake 3.14, I cannot compile this because I'm not up to date. But if I'm, for example, CMake 3.19, I can even go as far as running in 3.17 mode because that's the maximum mode that is compatible with this CMake list.txt file. At least that's what the developer says he tested it with and assures that it works in this case. And the reason for that is you might have some special behavior if you are supporting a newer version with some special features. It depends on you. So this is what you can do. I would recommend to always use the newest version of CMake as your binary, because there's no reason to use an old version of CMake, because they are really good in backward compatibility. But at least I would say, put in your CMake minimum required file the 3.15 version. The reason for that is all the features I will show you require at least 3.15. You don't have to, but if you don't have to support old versions of CMake, which I don't know why you should, because you can always either download the source and compile it yourself or get pre-compiled versions. For example, there's also for Ubuntu and Debian users an apt repository, apt.kitware.com, I think it's called, from the makers of CMake, where you can always get the latest version, and that should be just fine. So use at least a more recent version. Okay, and then if you have that in your CMake list.txt file, in all of these, you want to declare a project saying, hey, this belongs to this special project. You give it a name here, you give it some version number, maybe some description, what it is, some UL where you find more information or whatever, and you can always tell it what languages you want to compile the sources for this project can be. By default, it is C and C++, but you can add more. So put this as early as possible after the CMake minimum required keyword. If you're omitting that, I think CMake will somehow create some artificial project call there. I'm not sure how it's handling it, so better don't forget it. And what it does, it sets some variables that you could use, and also CMake uses itself with the things you gave it there, some project name, version, etc. And as I said, C and C++ are supported, but you can give it some other stuff. Even Java is supported as far as I know. And if you don't want to have, for example, support for C, just for CXX, just for C++, use the languages keyword there with just CXX. So you're saying C files are not used there, or they are interpreted as C++. Actually, I don't really know what it does there. And yeah, that's how you can restrict that. But as I said, put it as early as possible there. That's not really true. I would recommend to have something before that, and that's why I had left the space there, and that is to include some meta information. You realize here, this is just some path here. CMake current list here means, okay, relative to the current file we are in, the directory assume there's some file. In this case, it's called project -meta -info.in. And there you get some variables which are set here upstairs, there on the top. Instead of hard coding it there in your CMake list.txt file, you get this from this file. And the reason for that is maybe you want to change the version frequently, but you don't want to put this into your history, Git history of your CMake list.txt file, because it's just the version number or so. And maybe you're also automatically increasing that number by your build system or for whatever reason, so you're providing it from somewhere else. And that's a way how you could do that. Just with the include keyword, load another file where the information is, and then these variables you set there, use these there in the project call, and you are lucky and you can do that, and everything is fine. And this example, as I already said, it's relative to the current directory where we can find the project meta info file here in this case. Okay, this of course should be so that each and every CMake list.txt file calls its own file, its own meta information file. If they all would call the same, that's useless, and they have all the same project version and everything, and that doesn't make really sense in general, I would say. So this is something you should keep in mind. However, it is tedious. You have to remember to always type that, and it's boilerplate, and you probably don't want to have that. So there's some other way nowadays. You could just set a variable at the very top level CMake list.txt file called CMake project include before. Give it also some path, but in this case, it's a path to a common file. And what it does is, every time the project keyword is encountered, so the project command is called, the first thing it will do, it will load this file. No matter in what subdirectory you're calling project, it will always load that file. And what that file should look like, or probably do, is just having the include command from before. And this time, by the way, that's how it should look like. We've seen that before. But this time, we use the CMake current source dir, not CMake current list dir. If you don't know, the difference is CMake current source dir says that is the directory of the CMake list.txt file we are currently processing, while CMake list dir says that's the directory of the file we are currently in. The file we're currently in here is common project info.n. That's on the top level, but that's not what we want. We want the path relative to the current CMake list.txt file. So that's why we have to use that variable there and don't interchange it, or we have some problems. So that's some way we could do that. And that means the sub-level and top-level CMake list.txt files look pretty much the same. Only difference are there, of course, the comment at the top. Then the top-level CMake list.txt file has this set CMake project include before command, and the other ones, and they have different names for their project, but except for that, they're the same. This common include is the same, exactly, it's the same file. It's not a copy, it's still the same file, it's just one file there. While for the additional information that it loads, there each subdirectory, each CMake list.txt file should have its own. So that's something you could use. You might have noted, if you are going to use the trick with what I told you at the beginning, with using some other CMake list.txt file as your new root, this might break there, because then you don't have the CMake project include before called. And for that situation, you have to do that a little bit differently. Maybe use the include way I showed you, or get this information somewhere else. But there are some ways. And you can ask me afterwards if we have time, maybe. Okay, so that's how you might start it with a new project. But then, of course, you're not declaring your own targets only. You probably have some external dependencies which are already built and on your system. And a good example for that is Boost. You're always using Boost. As far as I know, everyone seems to use at least a little bit of Boost. And so you should find that. And there's something that should be used, which is the find package command. That's not only for Boost, but for libraries, external libraries in general. And that's what I showed you last year. My recommendation is to make it clean. If you have a bigger project, you could, of course, each sub-level CMake list.txt file could look itself for boost and load the components it needs. But if you have a bigger project, then you're doing this over and over again, and CMaking takes quite some time. We had this in our company. And instead of that, I recommend just put this in one, maybe sub-level directory and load it once there, get all the stuff you need from Boost, and then at the end, make these targets. They create imported targets. These are nice targets you can use in CMake, but with the only thing you don't have to build them. You can just use them on the right-hand side in the target link libraries command as a dependency. And then I would say make these global, because you don't want to have it just only in this subdirectory and the ones below, but you want to have it above maybe too, and in some parallel directory path there from the current location. So set the imported global variable, property to true, and this promotes these targets to a global scope. And so they are available everywhere. That was my recommendation last year. It's still something I recommend. And if we are looking at the find package call of Boost, what we have to do before was always setting some variables so that the find package command knows what kind of libraries we want to have there. That's still the same. And in general, if we are omitting that or we're setting it explicitly like we do here, we are using the so-called module mode of find package. This is find package looks for a file called findboost.cmake, which, by the way, comes with CMake itself for quite some time now. And there, these boost targets are created, and you give it some hints maybe, and it will find, hopefully, your boost libraries on your system, will create the targets, and everything is fine. And however, what is if you have a quite old CMake version, which you shouldn't have, but your boost version is more recent than that? Then the find boost CMake file does not know about the version, does not know what this thing is that's important there. So you have the boost additional versions variable there that you could set to tell it, hey, there is also a version 1.72 maybe that you should look for, so that's fine. But if your CMake version was so old and therefore the find boost script was so old, it doesn't know what new libraries might come there, or maybe some dependency between libraries have changed. If you think back, the Boost file system library always had a dependency on Boost system. And for a long time, Boost system had to be a compiled library, so you had to link this in. At some point, Boost system became header only by default, so Boost file system is still using that, but it already used because it was used during compilation, so you don't have a link dependency there anymore. But if your find Boost CMake script doesn't know that, then it will try to add there some dependency that is not there, so it will fail. There might be some other reasons. So this is not what you really like to have, and this is especially error-prone for the reasons I said. And there's a solution for that, and that is the so-called config mode of find package, which you should use preferably if it's possible. And the thing is, you just use the config keyword instead of module. And the thing is, for Boost itself, this requires you to use at least Boost 1.70, because you have to, the library you're looking for has to provide a library name config.cmake file. And that's what Boost is doing since Boost 1.70. So what find package does then is it looks for this file, and if it finds, it's lucky, it's happy, everything is coming from that file, and it knows what it has to do. And it will create the imported targets that you want to have there. Note, however, the header-only target that you created before was called Boost Boost. The new name that you should use is Boost Headers, so Boost : headers, but there's still an alias, so to be backward compatible. But that's what you should use. If you're using the new mode, just change your code, your CMake code, to use that too. And the Boost additional version variable is no longer used. You can just remove it. So that's good. And that means this is safe for all versions of CMake. You don't care what version of find Boost CMake script you have, because you're not using it. And so that's a good thing you want to have there. It's even working hopefully I haven't tested it, but with versions as old as 2.8.8, because that's where, at least in the documentation, where I found the first occurrences of the config mode of find package. So that should have worked for quite a long time, but as Boost didn't provide this config file at the beginning, that didn't work there. So that is a great thing, but there's one thing. I said you have to explicitly specify the components, as I did here. The components here are the binaries, the libraries you have to link. For the header-only stuff, you didn't have to put anything there in the components part of the find package command. You could just call it without anything, and you get the Boost headers or Boost target for free, and that's all the header-only files. But I recommend that you start using adding the headers component there, even if you're just looking for the headers. And because you're more explicit, and maybe in the future, this is currently debated, there will be some changes so that the default behavior of calling the find package without any component might try to get all of Boost into. So create targets for all that it can find and belongs to that version. This is probably not coming within the next few years, but it might come. Yeah, and speaking of which, I said you have to be explicit. What is if you want to have all your components, at least all your compiled libraries found there? It will probably just look like this. And that's not really what you want to do, especially if with newer versions there might be some new library that you have to put into the list, and that's just tedious and error-prone. So luckily, with the not upcoming, I must say, Boost version, because the next version that's currently in release candidate mode or beta mode, I don't know, is Boost 1.72. But with 1.73, there will be a new component available, which is called all written with capital letters. And doing that is just what I showed you. It will look for all the files that it can find there. That doesn't mean it finds all the components that belong to Boost, only the ones you have installed, because you know, at least with your package manager on your Ubuntu, maybe you can just install some of the Boost libraries and omit the rest. And it will find all these, but not the rest, of course, because it's not installed. But if you install everything, it will find everything. And the nice thing is, it also gives you a nice target here. It's called Boost All Targets, and a nice variable, sorry, which is just a handle for all these targets. It contains the names of all these targets. And so there's some nice way of promoting all of these targets to global scope, as I'm still recommending to do that if you're calling from a subdirectory, which is cleaner. So that is a nice thing. And it's even getting better, because if you have the required keyword in the find package command, you can omit the components keyword, and now it just says required all, which I would say is pretty much self-explanatory, and you could just use that. So that's how you get Boost. And for other external libraries, it's probably similar, as long as they provide the library name config.cmake file with it. And so I recommend you using the config mode if possible. By the way, if you're omitting the keyword, I said by default it's using the module mode first, and then if it doesn't find it, using the config mode. You can switch this order, but you don't have to. And especially for the find Boost script, it will, even if it's running in module mode there, the first thing it will try is find some config file for it, and if so, then it behaves as if it was run in config mode and just create the targets from it. So in general, you should be safe with find package, just calling it without any of these keywords, as long as you're using at least 1.70, and then we'll use the config mode implicitly. Okay, that's enough for Boost there. Now, external dependencies, there might be some others that are not built already that you might have to build with your project together, and that's also a solution. And to have a quick use case, sometimes it's just not feasible to have a pre-built version, and the reasons are, there are multiple ones. Choose what you like, but some might be that you need some special compiler flags when building this, and these might depend on your target, because you want to compile everything on your project. You want to compile everything with the same targets there, maybe just enabling address sanitizer or something like that. And it's or you say it's not general enough to have to do something there. So there are multiple reasons. And the solution is to build it together with your project. Then you might say, okay, so I have to check out the code maybe while I'm building. Okay, but wait, I want to use some of these targets that are coming from the project maybe while I'm configuring. But when I'm doing that while building, that means during compilation. That's after I CMake. So how should I do this stuff? And to the rescue comes the FetchContent CMake module. One important constraint. This only works if your dependency, your external dependency, is also using CMake to build. If it's not using CMake, you cannot use this way. But as CMake seems to be the de facto standard in our C++ world, that should not be such a big of a problem, I hope. Okay, let's look at this with a real real example with Google Test. That's also what is in the documentation of FetchContent, by the way. So the first thing we have to do is load the FetchContent module. Note we don't do this with find package, we do it with include. And the thing is, because it's coming with CMake, we can go this way, and it's in CMake since version 3.11. So if you're using a more recent version, which you should do, there should be no problem finding that module and using it. So the next thing you have to do is declare your a target, a handle for your, not a target, a handle for your external dependency. Give it a name. I said here just Google Test. Give it some location where you can find. You can either download it from some location or, in this case, check it out from some Git repository. There are multiple ways. By the way, if you're more familiar with all this stuff, FetchContent builds on top of the external project module and is able to use the features for downloading or getting the sources that that external project provides. So you can look it up there. In our case, assuming everyone is using Git itself and Google Test is using that, we are using the Git there. And then, at the end, we just have to make these CMake files available of the downloaded source, and we're doing that with the FetchContent make available command. And that's what you should use in general, and that's pretty much all. If you're doing that, you are having your CMake list txt files of your Google Test here, and it should declare the targets, and when you're building it, it will build them with your target, and you can link against it, and you're lucky and fine, and everything works. In general, because this might not work always, especially you might have to set some local modifications on the source you downloaded, and if you have to do that, you should expand the macro we've seen before, the make available command, and this is what it looks like. It first checks, did we already populate that code? Means, did we already download it from some other CMake list txt file or so? If not, we're populating it, getting the source, and then we can do our local modifications, the orange part here, and at the end we just have the add subdirectory command, means make this the CMake list txt file of our code, in this case Google Test, available to our current CMake run. Okay, that's how it is done. And yeah, that's how it should look like if you zoom in. But there are some problems with Google Tests, sadly. Because Google Test is using some quite old-fashioned CMake list txt files. And you are probably getting some warnings like this. And it's saying here, okay, policy CMP 0048 is not set. And what this policy says is, the project command, we've seen that before, is managing the version. But sadly, you didn't give us a version in the project command. So what should I do? There's an old mode where you can use it yourself. There's a new mode for that policy where you say CMake should use that and I don't care. And there's no mode, which we have now, which is it's not set, and CMake doesn't know how it should handle it. And it does something, but it says, hey, that's difficult and dangerous. Be aware of that. But maybe I just don't care. And so there's a hint, use the -w no def CMake command line argument to suppress that. Okay, let's try that. And no, wait. how should I do that? How should I call this through fetch content? Because CMake is already started. And the simple answer is we cannot. So there must be another way. So maybe let's use the CMake policy command and before we are getting the sources and making it available and just setting that. Should be working, shouldn't it? But that's not working either. And the reason for that is a CMake list.txt file of that one has a top-level CMake list.txt file, so it has the CMake minimum required keyword in there, which, by the way, I'm still recommending to do that in all your files, but here it bites us. And especially because it's a really old version, which I don't recommend to use in your own CMake list.txt files, 2.6.2, I'm not sure from when it is, 2008 or 9, I don't know, maybe even older. So this is not working. This will reset all the policies, and because CMake policy 48 didn't exist at that time, that's unset. So that is unpleasant. So do I really have to patch it? And the answer is luckily no. We can use something we've seen before, the CMake project, and then the project name include before. We've seen the CMake project include before. Now we have a specific one for a specific for a specific project. And what it does, if you load this file similar to before, it should just set our CMake policy. And as we are saying, this is done at the beginning of the project command. Our project command should be fine because it finds some policy 48 and it is set, it's not unset, so that should just work. And by the way, you first have to find out what the name of the project is. In our situation, the top level CMake list.txt file of Google Test is called Google Test minus distribution, so I have to put in that there. And if I'm doing that, that's just working, so great, we found that. And as I've mentioned this now twice, a quick interlude, there are two of these commands. The CMake project include before, we have seen before, so this is the very first file that is loaded when you're encountering any project call. And there's the CMake project include, which is the very last thing, which is called where this file is loaded after the project command. So the one on the left-hand side before and the other one on the right-hand side after the project command. And these both came into CMake in version 3.15. So that's, by the way, why I'm also recommending at least 3.15. But there, even what I've shown you, CMake project with the project name include before and, of course, the version without the before. These are similar. The only thing is, first comes the general one before, then the specialized before, then the project call, then the specialized after, and then the general after. So it's going like a new this way. And if we're looking at the include is even quite old. It's coming from 2.8.9 version of CMake, and the other one is in 3.17. And that's a problem, because currently we have release candidate for 3.16, so this is not exactly available now. So, revisiting our problem we had. This here, as I said, is not working, as long as we are having 3.7, not 3.7 or newer. So what should we do? And luckily for this specific problem, we have a solution, because we have here, I would call it a policy problem. And for that, there exists a simple way, and also quite long, which is set a default value for a non-set policy. And that's what we should do here. And we're doing that by setting this variable, CMake policy default underscore CMP, and then the number, so 0048. If we're doing that, finally, it works, and it should work with quite some old versions too. And by the way, be aware, if you are using the CMake project include or include before command, as I recommended when I showed you how to start maybe a CMake project, this will also be called when you have something some content got via fetch content, because this is now in your CMake list hierarchy. So what it does is it tries to load a file which is not there, because we said, load the project meta info in, and Google does not know anything about it. So that's inconvenient. And the only solution I currently have is you have to unset this variable before the fetch content make available call, and then reset it afterwards. That's sad, and maybe this should be done by FetchContent Make Available itself. We'll see. I will probably provide some issue requests there and talk to the author, Greg Scott, and maybe he will decide, or I just propose it, I don't know, to have this automatically done. We will see, or give it some extra argument to the FetchContent Make Available call. We will see, because this might happen quite often in the future. I don't know. Okay, but we are still not done with Google Test. There's one thing I forgot to mention, and this is the recommendation nowadays is to use the namespace syntax we've seen with Boost for targets, which is Boost, double colon, and then the component you're looking at. And that's not, the targets of Google Tests are not using that. They're just one name without the double colon thing. And also the usage requirements for the automatic propagation, which we want to have in modern CMake, is also not done completely, especially because with Google Test you're also getting Google Mock. And Google Mock builds on or requires a Google Test, but this dependency is not set. So what we have to do is to create aliases with the add library, our alias name, alias keyword, and the original target. And here we're doing that for the namespace syntax. And we also have to declare a dependency to getting the usage requirements from the Google Mock target to the G-test target. And so we should be fine, shouldn't we? But sadly, we are not. And the reason is something I mentioned before. CMake will complain, this time with an error, not a warning anymore. And it says, all users of targeting library command, I mentioned that before, you might remember, with the target must be either all keyword, so having private, interface, or public, or all plain. And the problem is, in the CMake list txt files of Google Test, that was already used with the old signature without the keyword. So we have to do the same here to please CMake. So that's the only situation where I would say it should be okay with omitting the keyword, but in general, don't do that. Still my recommendation. Okay, to wrap it up, what should you take home from this talk? Of course, use modern CMake, but you probably are here because you want to do that, or you're already doing that, so that's nothing new. I'm still recommending use the newest CMake version, the binary at least, because there's no reason to not do it. I told you already. I would say use at least CMake 3.15, which is currently still the most recent one, but 3.16 is already there, and the other ones are coming. I think there will be about 3 releases per year in general, so, and some sub-releases with some fixes maybe too. So go for the latest. There's no problem in not doing that because they're backwards compatible. Use find package if you're looking for external dependencies, but use it in config mode if possible. That's safer. That's how the developer wanted it. And that's also where CMake wants to go. They want to deprecate the find boost module, CMake script, for example, the module script there. And I think in maybe in 2 years or so, that will be really removed or so. We will see. But use that if you can. And then if you want to build an external dependency, use FetchContent. I've showed you that, but be aware there might be some problems. And if you want to reduce some boiler code, try to use the CMake project include or include before and the other thing with the keyword there. But beware of the interaction with FetchContent that you might have to unset one of these variables before. And yeah, with Boost, I would say always use the component full version, so always give the component keyword and then at least the headers. If you're only looking for the headers, don't use it without components because that might change in the future. And with that, I would say I'm done. That's all, folks. If you want to know more, there are some good resources on the internet. There's, of course, the CMake reference documentation, which is what I said there. It's more of a reference. It's not something you want to learn it with, but you can look up stuff there, and it's really good if you're looking for specific things. If you want to learn it by heart, and I can really highly recommend Greg Scott's book, Professional CMake, A Practical Guide. I did this already so often here. It's sad that I don't get any money for doing that, but That's a really good book, and it's worth its money. I think it's just about $30, $35 or so. It's not much, and it's really worth it, and it's updating constantly, and you're getting the updates for free. He also gave a talk last year this year on CPPCon, which is worth looking at. Actually, he's talking about stuff that I thought I wanted to talk here, but I didn't, and that is symbol visibility, versioning, installing, and the RPath variable, which might interact there. So look at that. And then, of course, there's my talk from last year. I recommend, if you want to see the difference between traditional and modern CMake and also have some examples, look there. The examples from my last talk you will also find in the link I gave on the title page, where you can also find the slides from last year and the slides from this year. And you can play around with that. And with that, I'm done, and I think I'm pretty much over. So sorry, can take the questions afterwards. So thank you very much.